There's still people turning up, but I think in the interest of time, we can get going. So welcome everyone to the Cross-VESRI Journal Club for August 2023. Speaking this evening, we've got, this morning, wherever you are, depends. We've got Einar Ólason from the Stiftelsen Nansen Center for Miljö og Fjernmåling, which I believe is the Environmental and Remote Sensing Center. I can work out some of the words because they're a bit like Swedish. But yeah, Einar is on the SASIP project, and he's going to be talking to us about some of the work they've been doing and thoughts around parameterizations for sea ice. So yeah, whenever you're ready and you want to share your slides, Einar.
Thank you, Jack. Thank you. Yeah, it's usually just the Nansen Center for short.
Okay, Nansen Center.
Yes. Okay, so I will share my screen and slides. So what I want to talk about today is a bit the title is a bit grandiose in the sense that but it's really this sort of basic ideas behind what we're doing with when it comes to large-scale modeling in the SASIP project. So the idea is that we need to build a new rheology for sea ice, and of course this is not a new idea. It's been coming for a while now, more than 10 years. But the SASIP project is sort of the push that we need to get it out into the out of our sort of basement kind of area, out of our little lab and out into the world, I would say. And what I wanted to talk about is the kind of philosophy behind this, and the philosophy behind why we want to have a different approach to the common approaches that's used today. So just as a slide, as a short overview, I'll talk a bit about what sounds like a bit esoteric thing, which is the scaling of deformation. So what is it and why do we care? This leads us to development of damage propagation models, which is what we are using, and I would like to show you how these things are linked, and how the physical understanding we gain from this deformation spatial scaling helps us, or has helped developing this new model. And then towards the end, I wanted to talk a bit about something a bit more speculative into the gray zone. So what happens when you enter the gray zone between scales, where you have to switch from one type of model to another type of model because you have a different physics at different scales. Right. So first of all, this talk is about sea ice rheology, and rheology is the internal stress term of the momentum equation. So I have here first of all, I have a laser pointer. Right, so we have here the momentum equation for sea ice. It's just Newton's second law. Momentum, or the force is equal to the mass times acceleration. And here on the right-hand side, we have various external forces. So the atmosphere and the ocean drag on the ice, Coriolis force, the force due to tilt of the sea surface. But the key interest here is the internal stress, so the gradient of the stress tensor, which is sigma. And this term, it decides or dictates how the ice responds to the external forcing. So all the terms to the right of the stress term, to the right of the stress term, are external forces or body forces in a sense, and the sigma term here, it says how does the ice respond when the wind blows, when the currents flow? Does it break? Does it flow? Does it or is this just stuck there? Models today, I think, I should say that basically all models today are using the viscous plastic rheology, which comes from Hippler in '79. But we're developing something different, which we're calling brittle rheologies. And then there's a bunch of shorthand of notations here, which we'll get into. So to start, maybe stepping a bit back, give a brief overview of sea ice dynamics models. Then here on in the upper part is what people are using today, I would say, and it all stems back from the Ajax model from '74, which was an elastic plastic model, quite conceptual, but still describes some of the basic ideas that we're still using to describe CS dynamics today. Then the viscous plastic model, which was developed by Hippler, is a direct derivative of the Ajax model. Basically, you take what was an elastic plastic model, so you have an elastic solid that can break, and you replace this elastic term with a viscous term. So it's a very, very, very viscous fluid that can break. It's a bit of a funny material in a way, and it's almost like an extremely extremely thick mayonnaise or toothpaste in a sense. And the physics in this is what people are using today. There have been made some basically numerical improvements. I mentioned here the derivative models that I've listed here. They're all numerical improvements on the basic physics that are present in the Hippler model. So when you see this VP or EVP or MEVP, it's all the same physics, but different numerics, essentially. Now, what we're doing is substantially different in the sense that it's not directly derived from the Ajax model. It has some commonalities, but it's not directly there. So that's why I put a little dash line. And it starts off with the elastobrittle model in 2011 from Girard. And then the physics itself is developed largely in France, in Grenoble. The elastobrittle model is followed on by the Maxwell elastobrittle model by Dansereau in 2016. But as a sort of a side development, we at the Nansen Center in Norway, we developed the neXtSIM CS model, which is a full-scale model and uses these rheologies that were being developed in France. So we take these ideas and we try to put it into a large-scale model with all the problems and all the opportunities that entails. So that's Bouillon and Rampal and Rampal et al. We would try we're building a full-scale model based on these rather conceptual ideas, I would say. But then here in 22 and last year, these two branches sort of merged again, where we at the Nansen Center, we saw that we could learn things from the large-scale models and actually improve the physics themselves. So that's a bit the history. We go back a bit even further. Why do something different? And the reason is the video you see on your right. So this is satellite observations of sea ice shear deformation. So it is the shear motion of the ice. So where you see bright red colors is where the ice on the left is going in the opposite direction to the ice on the right. So it's a shear zone. And what you see is that the shear zones are extremely localized. They are very long, and they are very intermittent, so they come and go quite rapidly. And when people first saw these images back in the late 1990s, early 2000s, it was quite clear that this was nothing at all like what you saw in the VP models of the day. It was something completely different. It was something that was obviously not being captured by the models. So that's one rationale is that we want to reproduce what we see in the observations. But these are also very important features, because where the ice is shearing like this, it's breaking. It may open up and form leads. It may converge and form ridges, and this is what really separates the real ice cover from a homogeneous, quite ice cover, which is what we see in climate models today. So this in the typical climate model, there's a lot of physics missing, which we see here in these images. What's interesting and problematic with this is that these lines are generally called linear kinematic features, or LKFs. And these LKFs, they have a stochastic component. So unless you know precisely the initial conditions, there's no way you can simulate exactly where the lines are going to form. And even to spoil a bit, we have a model that can do this more or less, but change a little bit the initial conditions, and you get a very different, or not a very different, but quite different location for the feature. So we can't expect our models to reproduce exactly the patterns that we see. What we can expect is that we reproduce the statistics. And one of the statistical methods, and the one I'm going to talk about here today, is what's called the scaling analysis, which is appropriate for fractal systems, which it turns out this actually is. Okay, so what is the scaling of deformation, and why do we care? So first of all, the spatial scaling, we can just talk about it as a statistical method, a method to retrieve some statistical information about the field that we just saw. So what you do, simply put, is that you consider how the mean, variance, and skewness of the PDF of deformation rates, how this depends on spatial scale. So you take one snapshot of the field I showed you before, you calculate, or you plot the PDF, and you see how and you describe its shape by the mean, the variance, basically the standard deviation, and the skewness, so how long the tail is. And you do this at different scales. So first you take the image as it is, and you do this analysis, and you get 3 numbers. And then you do a coarse graining. So here I've drawn up something that looks like the image, so a bunch of pixels, and you just average over you average across the, oops, yeah, it didn't work. So you average the 4 neighboring pixels, and you get a coarser image. And you look at the PDF, you calculate the mean, the variance, and the skewness, and so on. And when you do this, and here's a figure that we did a long time ago, actually, you see that here is in the upper left is the shear rate at the original resolution, and then you coarse grain it, and you see that you start to lose the extreme values. And what you see is that what was clearly a distribution with a very long tail, so you have a lot of pixels with very, very high values up in the left corner. Down in the right corner, you have much fewer of these high values, and you have a much more Gaussian kind of a shape. So you do this for different scales. So here's a plot from Massan et al., who did it, who were the first to do this for sea ice. Here you have it at the scale of the observation, so at the satellite, the scale which the satellite sees it. And then the next column here is the coarse-grained once, twice, and so on up to 1,000 kilometers. So first, each box is 10 kilometers, and then here at the end it's 1,000-kilometer boxes that we're calculating the moments of the distribution. And you can see that you can draw a straight line through the points for the different moments. So here, moment equals 1, that's the mean. Second is the variance, and the third is the skewness. And without maybe going into a lot of details, what this means is that the system is fractal, and when the points fall on a straight line like this, we say that it scales in space. And you note that this is a log-log plot, actually. Secondly, you can look at the slope of these different curves and plot that as a function of the momentum order. And you get this this function here with beta. Now, what people have done is to do this analysis for the observations, and then do this analysis for the models and compare the two and say, you know, my model is good if it reproduces this, and it's not good enough if it doesn't do that. But I wanted to also talk about what it is in the physical sense. So first of all, this spatial scaling tells you that there's a link between deformation at different scales. So the deformation at the coarser scales somehow knows what's happening at the finer scales, and the origin of the scaling is probably what's called a multiplicative cascade. It's not an easy word for me, but what it means essentially is that the deformation that we see at the coarser scales, it comes about because there's lots of small events at the fine scale which then propagate up to the coarser scale. So the small events, they trigger larger events, which then trigger the dominating events at the coarse scale. And secondly, this the structure function here, the beta, the fact that it's not a straight line, but a second order fit, it tells us that this is a multifractal scaling, which tells us also that the more intense events are more localized. It's the same as with earthquakes, and actually there's a lot of similarities between sea ice mechanics and crustal mechanics. And in this case, it's the earthquakes. The large earthquakes are more localized. They're always in the same place, or the smaller ones are sort of scattered around. And the same for ice. Okay, so now we have this analysis method of the field. So what do you want to do with it is the question a bit. You can do model evaluation like I talked about, compare modeled and observed slopes and patterns and so on. You look at the scaling exponent, you look at the degree of multifractality, and there's people who've done that first. I think first probably was Girard in 2009, and the latest one I know of is Bouchard paper in 2022. It is a nice thing to do, but it's a bit limiting in my point of view. What I'm much more interested in is the physical understanding. So what are the processes that give us the scaling, and can we use this knowledge to build a CS model? Okay, and of course, also why are our models reproducing the scaling or not? And I want to dig a bit into the what's here on the right hand column, and because it links directly to the development of these brittle models that we are using, the standard propagation models. So let's say that we want to model this thing here on the left, this scaling of shear deformation. And it's the only thing actually we want to model. We don't care about the drift or the thickness or anything. We just say, okay, this is an interesting little thing. We want to write a model that reproduces that. Fine. So if we do that, we can actually just write down 3 simple requirements. Simple. First of all, your model should, or the model that we write, it should have a power law scaling of the deformation rates. So if you do this analysis on the model fields, you should get points like this that fall on a straight line. The slope of those straight lines and the structure function, this one should be the same as the observed one. And of course, the magnitude must be right as well. So you start off at the right point for each of the different moments. Now, this is observations, and this is reality. So in reality, we expect these lines to go down to some scale, which we don't really know what is. In the observations, it's 10 kilometers. That's the highest resolution that we have right now, although people are working on it. But 10 kilometers is the highest resolution. We expect this scale here to be quite a lot smaller, and I'll talk about that a bit later. And we expect that if we had observations down to that scale, we would see the line scale all the way down to that scale, and then we don't really know what happens at a higher resolution than that. Okay, so what we can safely assume is that our model is going to be of a coarser resolution than this this scale here, this Xi. In order to fulfill the first model requirement, then our model should, from that scale where it is run, it should reproduce this kind of behavior as is shown in red. The slope and the structure function should be right. There should be a power law scaling, and you should start off at the right point. Now, everything that happens to the right of X here is dictated by the grid scale physics. So interaction between different grid cells, because it's at a spatial scale that is coarser than the model resolution. What happens in the circles must be determined by a subgridscale parameterisation, because that's the only information you can have. You cannot determine that from what's happening around you. It has to come from a scale that is smaller than the grid scale. And in 2011, Girard et al., they proposed a model that fulfills these requirements, the elasto-brittle model. And they said, although I'm rephrasing, but they said that the subgrid scale here is what's called progressive damage modeling, which I'll tell you about later. And the grid scale physics is long-range elastic interactions. So they proposed that the ice be modeled as a damaging elastic sheet. A very, very simple concept in a way. It's just you have an elastic sheet with elasticity E, and you can damage it, and when it's damaged, you modify the elasticity. So the elasticity is a function of y, which is the Young modulus, which is a constant, and 1 minus d, where d is the damage and goes from 0 to 1. Now, you set up your model and you calculate the stresses at all the grid points. And here, below we have the stresses in the normal and shear stress space. And I've drawn also an envelope here, which is the more Coulomb envelope. And the idea behind this progressive damage modeling is that as long as the stress in the grid points is inside the envelope, nothing happens. It's an elastic response. It's a physically reasonable state, so it's fine. However, there will be points which are outside the envelope, and this is not a physically permitted state. The material cannot sustain stresses that are outside the envelope. So to respond to this, what you do is you increase D, you weaken the material locally at each grid point. And what Girard did was to iteratively increase the damage until all the points in the model were either on the envelope or inside it. So then you have a physically permitted state for all the points, and you've solved the problem for that time step. And this is great. It works quite well. It gives you a nice temporal scaling, but this figure actually is not from theirs, from Pierre's paper in 2019, only because Pierre's figure is much nicer than than what Girard plotted. But it's the same thing still. We start off, so the model, the model is the CN, I think, and the observations are the black, but they're basically the same. You start off at the right point, right? So the subgrid, so the progressive damaging is a good subgrid scale parameterization, right? And you get scaling and you get the right slope, so the grid scale physics are also captured. So then, in a sense, we're happy. That's all that we wanted from this model to begin with, was to reproduce this. But what's interesting also is that it does, not surprisingly, give very localized deformation features. So here on the left, we have, again, the RGPS data. And you can see, and on the right is are the results from this EB model. And you can see that the shear rate in the EB model is very, very localized. Long straight lines, just like the RGPS. You can also see that that's a bit where the similarity ends. You have lines crossing like this at 90 degrees angles, but here it's clearly not 90 degrees, but something more like 50 or 45. And there are several things that are not quite right, but this is a very encouraging first start. And that's where we pick it up and we continue and we try to improve the model further, both in Norway with the neXtSIM large-scale realistic setups, but also in Grenoble, where Veronique Dansereau was worked on the Maxwell elastobrittle or MEB model. Instead of having just a spring, you add also a dashpot. And this is to represent stress relaxation and permanent deformation, instead of the reversible deformation that's only present in the EB model. And then our latest addition was to add also a friction element here to prevent excessive convergence of damaged ice. It's a lot of work that I'm not really going to talk about. It's going from the EB model to the BBM model took 11 years, and of a lot of learning along the way. But the core is still there. The core is still this simple idea of a subgrid scale parameterization of the stress relaxation and a grid scale representation of the representation of the grid scale physics as well. So that's the sort of the core, or where we're at, in a sense, in the development of this brittle branch. I wanted to brag a bit of how nice it's starting to look. So you can see here on the left are the satellite observations, they are GPS. In the middle are the results that we got from the BBM model, and we're in this paper. And on the right is a more classic VP solution. So this is all run at a 10-kilometer resolution. The models are run at a 10-kilometer resolution, and the observations are also at a 10-kilometer resolutions. And you can see that it's getting to look quite convincing. And we've also coupled this to an ocean model, when we've run quite long simulations and started sort of studying how interactions with the ocean and the atmosphere change when you change the rheology. So with the BBM, we have a versatile brittle model that captures the deformation scaling and spatial patterns of deformation. And also, actually, without showing you here, gives a good large-scale drift and thickness, and gives quite good results at different resolutions, which is a key point here, really, because if you have a good subgrid scale parameterization, you should be able to pick your parameters so that it should work at different model resolutions. And of course, we're also working on the atmosphere-ocean ice interactions. Maybe most importantly was the paper by Guillaume in 2022, but then a lot of work in SASIP is and will be centered around this kind of interactions, and also interactions with waves. So that's a bit the state of play, in a sense, how we and the background behind these new development in CS rheology, how we using this physics that we've learned about in the deformation scaling, how we use it to build a different kind of model from different kind of principles than what the previous generation was. I wanted to then, in the end, talk about something that's not really, it's a bit more speculative, I would say, and go a bit into the gray zone, a bit poetically, perhaps. The point here is that if we go back to the model requirements that I talked about, that we expect the model resolution X to be substantially larger than Xi, and then we have these three requirements of a power law scaling, slope and structure function should be right, and the magnitude should be right. I mean, these still hold, but the question sort of that inevitably pops up is, well, what is the value of Xi? What is this scale at the far left? And what happens when we start to approach it? And this is what is referred to as the gray zone. It's the zone between two model worlds, in a sense. So when you go from larger than Xi to smaller than Xi, what you have to do is basically you have to build a new model, different physics. And the way to approach this problem is through multi-scale modeling. So at the coarse resolution, we would use the kind of continuum models with the rheology like I just described, while at the higher resolution, you need something different. And this something different, I'm confident, and I think most people are confident, is that this something different is discrete element modeling, where you model each ice flow how it moves, how it breaks, how it's welded or freezes together with the other flows around, and so on. Obviously, an extremely complicated problem to solve for the entire Arctic, and it's not been done as far as I'm aware. It's mostly been used in the marginal ice zone, but there's some very interesting developments happening in the discrete element modeling world today. But the other question, because I think this is quite clear, but the other question is, so where is this limit? Where is this gray zone? And really the value of Xi is the size of what's called the stress concentrator. The thing, the feature, the fracture that concentrates the stresses in the material, that initiates the cascade. So at the lab scale, this is quite clear. It's the size of the fracture. So the fracture size is the fracture is the stress concentrator. For a Pan-Arctic large-scale model, it's not as obvious. It could be a lead. You can imagine that a lead, these long openings in the ice, would be your stress concentrator. It could be shear zone, and it's basically the same thing in a way. The collection of fractures and leads which form when the ice shears. But we don't really know. And we don't really have the observations. And we don't really have the models either. But we may be actually starting to approach this resolution with super high resolution models, which are being run today. And the only super high resolution realistic Pan-Arctic simulations we have are using the VP model, the old-fashioned model of Hybla. And it's actually interesting to think about these simulations, because the VP model implicitly assumes that all the features are resolved. So it doesn't really have a subgrid scale parameterization for the stress relaxation. It's not quite so clean cut. It does have a parameterization for the ice strength, but it's not quite the same thing. So we can sort of look at these VP simulations that exist at different resolutions with different models and try to learn something from them. So what do we see? Actually, interestingly enough, if you go to a really high resolution, somewhere around 2 kilometers, maybe a bit coarser if you ask some people, 4, but not much coarser than 4 kilometers, you start to see proper scaling emerging from these models. If you run them at a coarser resolution, it's all wrong. You don't get the lines are wrong, the slopes are wrong, the magnitude is wrong. It's not, it's all wrong. But when you go to higher resolution, something starts to work. Doesn't mean that it's completely right, but it's something is happening that is at least in the right direction, and it's quite interesting to think about. And to me, this indicates two things. Firstly, is that when you look at the model, which is the solid line here, you see that it scales, so it falls on the points here fall on a straight line. The slopes are reasonably good. So the grid scale physics are mostly correct in this model, which is very different from the brittle models. And the commonality between the two is essentially that both allow propagation of stress relaxation. So in both models, when you have a high stress in one grid cell, which then exceeds some limit, either the plastic limit in the VP model or the more Coulomb limit in the brittle rheologies, you release the stress and you change not just the stress state of that single grid cell, but also you allow this stress relaxation to propagate into the neighboring grid cells, because the neighboring grid cells know what's happening around them and can propagate this change in stress. And it really seems to be this sort of propagation of stress changes that generates these the patterns that you see on the left-hand figure. It also indicates that possibly for the Arctic sea ice, we have stress concentrators of the order of a kilometer. This is a bit less clear, I would say, but you would not expect this sort of a model to give this good scaling, as you see on the left, unless it really resolves the stress concentrators. It's really resolving the features that are initiating the stress relaxation, which then propagates across scales. Importantly, the analysis in both Hutter et al. And Boucher et al. Only goes down to the 10-kilometer resolution, so the resolution of the observations, and not down to the resolution of the model. Unfortunately, it would tell us a lot if they would have done that, but I think we can start to imagine that, yes, this is a clear indication to me that the stress concentrator is of the order of kilometer, and that is where we're entering the gray zone. So the model requirements more generally really are, well, if you have the scale, first of all, now the scale of the stress concentrator determines your model choice. So if you're at a higher resolution than the stress concentration, so here left of C, you need to have a flow resolving model, something that resolves basically everything. Okay, so a DEM model. If you're at a coarser resolution on the right, so everything that's basically more than a kilometer, you need a model that parameterizes the subgrid scale stress evolution, the red circles here, so that you start off at the right place, and then your grid scale physics can give you the right scaling pattern. So then to conclude, I showed you, I hope I convinced you, that spatial scaling of deformation can give you important insights into the CS dynamics at the basin scale. And we also seen that models that don't resolve the stress concentration, so models that are not of extremely high resolution, they need a rheology that gives you both subgrid scale representation of the stress relaxation and a grid scale representation of the stress redistribution. And the brittle rheologies are an example of this. It's not necessarily the be-all end-all of anything, but it's an example of this kind of a rheology. And we see clear indications that not just what I showed you here with the VP models, but there are other reasons also to think that this 1 kilometer, this is a critical resolution for the Arctic sea ice, this is where the gray zone is, the gray zone between two different types of models, so the DEM models and the continuum models that we use in climate models. Yes, so that was all. Thank you.
Excellent. Thank you very much for that, Einar. And it's interesting to see how those different models behave, sort of as you take them out of their comfort zones into other areas. If anyone has any questions, if they'd like to put their hand up, and they can ask their question, or if you can put it in the chat, either of those is good. Are there any